Welcome all to the course of Data Communication and Networking B7 semester Electronics and Communication Engineering. We are discussing Unit 3, a data link layer. Today we start a new topic called as a data link control. The two main functions of our data link layer are the data link control and the media access control. The first data link control deals with the design and the procedure of a communication between the two adjacent nodes, called as a node-to-node communication. We discuss this functionality in this topic. The second function of the data link layer in the media access control, or how to share the link, we will discuss the functionality of this media access control in the preceding lectures. Especially the data link control functions including framing, flow control, error control, and the software implemented protocols that provide smooth and reliable transmission of frames between the nodes. In this topic, we first discuss the framing, or how to organize the bits that are carried by the physical layer. We then discuss the flow and the error control, and a subset of this topic, techniques for error detection and correction, we will discuss in the preceding chapters. To implement the data link control, we need protocols. Each protocol is a set of rules that need to be implemented in the software and run by the two nodes involved in the data exchange at the data link layer. We discuss 5 protocols: 2 for a noiseless, just like ideal channels, and the 3 for the noisy or the real channels. Those in the first category are not actually implemented but provide a foundation for the understanding the protocols in the second category. After discussing the 5 protocols in the design, we saw how a bit oriented protocol is actually implemented by using a high level data link control, all called as a SDLC protocol. As an example, we also discuss a popular byte oriented protocol called as a point to point protocol, or PPP. So let's start with a first point: framing. A data link layer in the physical means moving bits in the form of signals from the source to the destination. The physical layer provides a bit synchronization to ensure that the sender and the receiver use the same bit duration and timing. The data link layer, on the other hand, needs to pack bits into the frames so that each frame is distinguishable from others. Our postal system practices a type of framing. The simple act of inserting a letter into the envelope separates one piece of information from the another. The envelope serves as a delimiter. In addition, each envelope defines the sender and the receiver address, since the postal system in many-to-many courier facilities. In a framing, in the data link layer separates a message from the one source to the destination, or from one message to the another destination, by adding a sender address and the destination address. The destination address defines where a packet is to go. The sender address helps the recipients acknowledge the receipt. Although the whole message could be packed in one frame, that is not normally done. One reason is that a frame can be very large, making flow and the error control very insufficient. When a message is carried in one very large frame, even a single bit error would be require the retransmission of the whole message. When a message is divided into the smaller frames, a single bit error affects only that small frames. So we can say that a smaller frame is very good for transmission compared to the larger frame. In this section, following topics to be discussed: a fixed size framing and variable size framing. A fixed size framing. frames can be fixed or variable size. In a fixed sign framing, there is no need for the defining the boundaries of the frames. The size itself can be used as a delimiter. An example of this type of framing is the ATM wide area network, which uses the frame of fixed size called as a cells. We will discuss in the later chapters. A variable size framing. Our main discussion in this chapter concerns the variable size framing, the prevalent in the local area network. In the variable size framing, we need a way to define the end of the frame and the beginning of the next. Historically, two approaches used for this purpose: a character oriented approach and the bit oriented approach. So our variable size framing will be divided in the two subtopics: character oriented and bit oriented. So let's start with a character oriented protocols. You can see the figure of the character oriented protocol over here. In the character oriented protocol, data to be carried are the 8 bits character from the coding system such as ASCII. The header which is normally carries a source and the destination address and the other control information. The trailer which carries the error detection or error correction redundant bits are also multiplies of 8 bits. To separate one frame to the next, an 8 bit or 1 byte flag is added over here at the beginning and the end of the frame. Fine. So one flag is entered over here and another flag is added over here to separate one frame to the another. The flag composed of protocols dependent special characters signals that start or the end of the frame. Our figure shows the format of the frame in a character oriented protocols. A character oriented framing was popular when only a text was exchanged by the data link layers. The flag could be selected to any character not used for the text communication. Now, however, we send other type of information such as graphs, audio and video. Any pattern used for the flag could also be a part of the information. If this happens, the receiver which encounters this pattern in the middle of the data thinks that it has reached the end of the frame. To fix this problem, a byte stuffing strategy was added to the character oriented framing. In the byte stuffing or the character stuffing, a special byte is added to the data section of the frame when there is a character with the same pattern as the flag. The data section is stuffed with an extra byte. This byte is usually called as a escape character, or you can say that over here, ESC, which has been predefined in a bit pattern. Whenever the receiver encounters the escape character, it removes it from the data section and treats the next character as a data, not the deliming flag. Fine. So it just remove this escape bit and consider 1, 2, 3, 4, 5, 6 is our data. Fine, at this stage. Okay. A byte stuffing by the escape character allows the presence of the flag in the data section of the frame, but it creates another problem. What happens if the text contains one or more escape characters following by a flag? The receiver removes the escape character but keeps the flag, which is incorrectly incorporated as the end of the frame. To solve this problem, the escape characters that are part of the next text must also be marked by the another escape character. In other words, if the escape character is a part of the text, the extra one is added to show that the second one is a part of the text. Our figure shows this situation. Okay, this error, it is an extra escape, then a escape is there, which shows that our escape is a part of our data. So receiver does not remove these escape characters. Okay, so we can say that a byte stopping is a process of adding a one extra byte whenever there is a flag or the escape character in the text. Fine, look it over here. Okay, a character oriented protocol presents another problem in the data communication. The universal coding system in use today, such as a Unicode, have a 16-bit or the 32-bit character that conflict with 8-bit characters. We can say that in general the tendency is moving towards a bit oriented protocol that we discuss next. Yes, important topic is a bit oriented protocol. In the bit oriented protocol, the data section of the frame is a sequence of bits to be interpreted by the upper layer as a text, graphic, audio, video, and so on. However, in addition to the headers, just like our possible trailers, we still need a delimiter to separate one frame from the another one. Most protocols use a special 8-bit pattern flag called as a 0, 1, 1, 1, 1, 1, 1, 0 as delimiter to define the beginning and the end of the frame, which is shown over figure. 0, 1, 1, 1, 1, 1, 1, 0, and same flag is there. Okay, this flag can create the same type of problem as we saw in our byte oriented protocol. That is, if the flag patterns appears in the data, we need to somehow inform the receiver that this is not at the end of the frame. We do this by stuffing a one single bit instead of one byte to prevent the pattern from the locking like flag. The strategy is called as a bit stuffing. In bit stuffing, if a 0 and 5 consecutive ones are encountered, an extra 0 bit is added. This extra stuffed bit is eventually removed from the data by the receiver. Note that the extra bit is added after the 1 0 followed by 5 ones regardless of the value of the next bit. This guarantees that the flag field sequence does not invariantly appear in our frame. Okay, you can see the over here. So we can say that a bit stuffing is a process of adding a one extra 0 whenever a 5 consecutive ones follow a 0 in the data, so that the receiver does not mistake the pattern for a flag. Okay. Yes, this figure shows sender and the bit removal at the receiver. Note that even if we have a 0 after the 5 ones, we still stuff 0 and we will removed by the receiver. Okay, so you just see there, it is our data and there is a 1 2 3 4 5 ones, a 0 is added, then once again a 5 ones are there, 0 is added. At the receiver you receive the same data and data will remove this 0 after these 5 ones and carry out this 2 1 over here. Okay, same thing is replied over here. This means that if the flag like pattern 0 5 1 0 appears in the data, it will change to 0 5 1 0 1 0 stuffed, and it is not mistaken as a flag by the receiver. The real flag 0 6 1 0 is not stuffed by the sender and the recognized by the receiver. Okay. Next point is flow and error control. A data communication requires at least two devices working together, one to send and other to receive. Even such a basic arrangement requires a great deal of coordination for the intelligent exchange to occur. The most important responsibilities of the data link layer are the flow control and error control. Collectively, these functions are known as a data link control. Okay, it can call as a data link control. In this section, following topics to be discussed: flow control and the error control. So start with our flow control. A flow control coordinates the amount of the data that can be sent before the receiving an acknowledgement and is one of the most important duties of the data link layer. In most protocols, flow control is a set of the procedures that tells the sender how much data to be transmitted before it must wait for an acknowledgement from the receiver. The flow of the data must not be allowed to overwhelm the receiver. Any receiver device has a limited speed at which it can process the incoming data and limited amount of memory in which to store incoming data. The receiving device must be able to inform the sending devices before these limits are reached and to request that the transmitting device send fewer frames or stop temporarily. Incoming data must be checked and processed before they can be used. The rate of such processing is often slower than the rate of transmission. For this reason, each receiving device has a block of memory called as a buffer reserved for storing information, the data until they are processed. If the buffer begins to fill up, the receiver must be able to tell the sender to hold the transmission until it once again is able to receive. Means one buffer is there to store the data temporarily. When buffer is also full, our receiver tells our sender that please hold the transmission or to stop the transmission. Okay, you can say that a flow control refers to a set of procedures used to restrict the amount of data that sender can send before the waiting the acknowledgement. Error control. And error control is both error detection and error correction. It allows the receiver to inform the sender of any frames lost or damaged in a transmission or coordinates the retransmission of those frames by the sender. In the data link layer, the term error control refers primarily to methods of error detection and retransmission. Our error control in the data link layer is often implemented simply. Anytime an error is detected in an exchange, specified frames are retransmitted. This process is called as a automatic repeat request or ARQ. This protocol we will see shortly. So we can say that an error control in the data link layer is based on the automatic repeat request ARQ, which is a retransmission of data. Protocols, very important. Now let us see how our data link can combine framing, flow control and error control to achieve the delivery of the data from one node to the another. The protocols are normally implemented in a software by using one of the common programming languages. To make our discussion language free, we have written in our pseudocode a version of each protocol that concentrates mostly on the procedure instead of delving into details of our language rules. Means we just make a general structure for our protocols, not going for in detail programming coding. We divide the discussion of a protocol in those that can be used for the noiseless or error free channels and those that can be used for the noisy channels or error creating channels. The protocols in the first category cannot be used in our real life, but they serve a basis for the understanding the protocols of the noisy channels. Our figures classifies protocol in the two categories: noiseless channel and noisy channels. In the noiseless channel, a simplest and a stop and wait protocols are there. In the noisy channel, stop and wait ARQ, go back and ARQ, and selective repeat ARQ. There is a difference between the protocols we discuss here that those in the real networks. All the protocols we discuss are the unidirectional in the sense that the data frames travel from the one node called as a sender and another node called as a receiver. Although a special frame called as a acknowledgement SEK and the negative acknowledgement NAK can flow in the opposite direction of the flow and the error control purpose. The data flow is only one direction. In the real life network, the data link protocols are implemented as a bidirectional. The data flow in the both direction can be possible. In these protocols, the flow and the error control in information such as SEK and NAKs is included in our data frames in the technique called as a piggybacking. Because bidirectional protocols are more complex than the unidirectional ones, we choose the latter for our discussion. If they are understood, they can be extended to the bidirectional protocols. So let's start with our noiseless channel. Let us first assume we have an ideal channel in which the no frames are lost, duplicated or the corrupted. We introduce the two protocols for this type of channel. The first protocol is does not use the flow control, and the second is uses the same. Of course, neither has error control because we have assumed that the channel is perfect noiseless channel. So there is no noise present over here. In this section, a following topic to be discussed: simplest protocol and stop and wait protocols as our noiseless channel protocols. Start with our simplest protocol. Our first protocol, which we call as a simplest protocol for the lack of any other name, is one that has no flow or error control. Like other protocols we'll discuss in this chapter, it is an unidirectional protocol in which the data frames are traveling in only one direction, from the sender to the receiver. In this type, we assume that the receiver can immediately handle any frame it receives with a processing time that is small enough to negligible. The data link layer in the receiver immediately removes the header from the frame and hands the data packet to the network layer, which can also accept the packet immediately. In other words, the receiver can never be overwhelmed with the incoming frames. Okay, so what is the design of our protocol? There is no need for the flow control in this scheme. The data link layer at the sender side gets the data from the network layer, makes the frame out of the data and send it to the data link layer at the receiver side, receives the frame at the physical layer, extract the data from the frame and delivers to the data link to the network layer. Okay, the flow is over here. The data link layer of the sender and the receiver provide the transmission service for these network layers. The data link layer uses the service provided by their physical layers such as signaling, multiplexing and so on for the physical transformation of the bits. Okay, our figure shows the design of the simplest protocol with a no flow or error control. We need to elaborate one procedure used by the both data link layers. The sender side cannot send the frame until the network layer has a data packet to send. Okay, when a particular packet is come, then it can send. The receiver side, it cannot deliver the data packet to its network layer until the frame arrives. Means a particular packet is arrived, then it will deliver the packet to the network layer. If the protocol is implemented as a procedure, we need to introduce the idea of events in the protocol. The procedure at the sender side is continuously running. There is no action until there is a request from the network layer. The procedure at the receiver is also continuously running, but there is no action until the notification of the physical layer arrives. The both procedures are constantly running because they do not know when the corresponding events will be occur. So particular event is there, request from the network layer. Over here network layer request is there. Over here the notification of our physical layer. Okay, so direction is shown there, up to down and down to up. Okay, so the algorithm, what is the algorithm? We will see. Our loop will be going on in a repeat forever mode in the both side. Yes, it is the algorithm at the sender side algorithm for the simplest protocol. The algorithm has an infinite loop, which means that the lines of 3 to 9 are the repeated forever once the program starts. The algorithm is an event driven one, which means that it sleeps just like in our line 3 until the event wakes up, like our 4. This means that there may be an undefined span of a time between the execution of a line 3 and 4. There is a gap between these actions. When an event request from the network layer occurs, the line 6 through 8 are executed. The program then repeats the loop and again sleeps at the line 3 until the next occurrence of the event. We have written a pseudocode for the main process. We do not show any details of our modules get data, make frame and send frame. A get data takes a data packets from the network layer. A make frame adds a header to the delimiter flex to the data packet to make a frame, and a send frame delivers the frame to the physical layer for the transmission. Okay, so it is the algorithm for our sender side. So it is the algorithm for our receiver side. So what is the process? In this algorithm, it has the same format as our previous algorithm, except that the direction of the frames and the data is upward. The event here is an arrival of a data frame. After the event occurs, the data link layer receives the frame from the physical layer using the receive frame instruction or a process that extracts the data from the frame using the extract data process and delivers the data to the network layer using the deliver data process. Here we also have an event driven algorithm because algorithm never knows when the data frame will arrive. Okay, so it is very clear to you how our algorithm works to our algorithm at the sender side and receiving side. So let's have an example to see it another way. Over here our figure shows an example of a communication using this protocol. It is very simple. The sender sends a sequence of the frames without even thinking about the receiver. To send the 3 frames, 3 events occur at the sender side and the 3 events occur at the receiving side. Note that the data frames are shown by the little boxes. The height of the box defines the transmission time between the first and the last bit of the frame. Okay, so it is an example of this our protocol. Okay, so we have completed our session over here. Up to now we have seen different type of framing and our simplest protocol. We will continue our discussion with our remaining protocol in a noiseless channel in a next session. Here is the question for you, which you have to write in your notebook and send back it to me as per the given direction. See you in the next session. Thank you.